from the previous lecture.
Yes. Because here from previously we assume in the introducing the closed form of the Hamiltonian, we assume that S is very large.
Yes.
I just want to know what do we really mean by large S, because as far as I remember spins, it's like an intrinsic super fictitious originally, because we are confused as to why electrons are occupying these levels.
Yeah, well, there is an atomic, the issue of atomic physics. It's the physics of the atom with the inner shells, like D shells or F shells, were very deeply located, very close to a nuclei. So they don't participate, well, they do delocalize, but not to the same extent as this S and P wave electrons do. Those create big, broad bands. There is a much smaller delocalization. These electrons are almost localized, very randomly undergoing hopping from side to side, and never go beyond near status because the overlap of the wave function is miserably small. Which means that you, with a very good approximation, can treat these inner electrons as localized electrons. And then you switch on to the quantum mechanics. You see the number of degenerate levels of orbital states, and you look at the spin states, and then you use the Hund's rules, and then you can build up the spin. For instance, you have 5 orbital states, and first of all, what you do, you put 5 parallel spins, parallel to each other values. You multiply 5 by 1/2, and you get 5 seconds, 5 halves. Is it large or not? 2.5. Sometimes number 2 is also much greater than 1. It depends on the type of the problem. You may have 7 halves and so forth. Don't be as pedantic as you may seem, because theoretical physics is based, you know what Landau would say about what is the theoretical physics. Theoretical physics is a very simple science. All you need is to find a small parameter. If you are done, then the second problem which remains to be done is to find the proper Greek letter to denote it. That's it. That's all what theoretical physics is about. So in those years, it was unimaginable to do something exactly, anything exactly. You would need to build up some kind of perturbation theory. So for that, you need a small parameter. In our business, in our case, the small parameter is 1/S. Why do we do it? Just to reply to your question, we know very well what the ground state is. The ground state, of a ferromagnet is a classical state. So therefore, we develop an approach in which we take into account quantum effects perturbatively, because classics gives us the right ground state. The eigenstate of a ferromagnet, all spin polarized, is an exact eigenstate of the Hamiltonian, which does not transform, is not coupled to any other state. It's an exact eigenstate with the minimal energy possible. All the other states are excited, and of course then you need quantum mechanics. So the quantum mechanical effects are measured by this parameter, which means that if the ground state, the ground state energy, if you remember, of a ferromagnet is proportional to J, S squared, and then maybe the dimensionality of the space, so it's of the order of S squared. So therefore, the excitation energy, typical excitation energy, must be of the order of J times S. So the ratio of this over that is of this order. And you drop all the other terms. And with this accuracy, it turns out that you have the notion of magnets, which are elementary excitations of the weakly excited ferromagnet. Elementary means that these excitations, in a very good approximation, can be regarded as non-interactive. It's an ideal gas of boson particles with some energy epsilon of k, and these are elementary excitations whose number is not fixed. It is at your disposal. It's like phonons or black body radiation at the sea. But we convict systematically all the hierarchy of the states and switch on the standard thermodynamic rules, the standard Gibbs hypothesis, and calculate any of the thermodynamic quantities of interest. So it's a very good basis to do calculations. And here again, what is most important perhaps is that whereas at the high temperature you have individual spins whose thermodynamics is exhausted by the Curie law, the magnetization is simply proportional to the field applied, with the proportionality coefficient being the susceptibility. At low temperatures there is nothing like this. Individual motion of the spin should be forgotten completely. Only collective degrees of freedom remain. Every time you overturn the spin by some external time-dependent magnetic field or whatever, what happens next is delocalization of the spin reversal. It delocalizes and transforms to a quasi-particle. And the quasi-particle is already a collective effect. All the spins participate. Yeah, so this is, we wanted to make much more progress in all this by deriving the so-called equations of motion. That means that we start with the local magnetization, the operator for the local magnetization, and write down in the Heisenberg representation and derive the equation of motion by calculating the commutator of this operator with the Hamiltonian. So again, the Hamiltonian of our problem is, let me write it down like this, minus 1/2 J, absolute value, summation over all lattice sides, summation over nearest neighbors, and here we have the exchange of direction S and Sn plus J. All right, and now here we have summation over n, omega naught dot Sn, where omega naught vector is a geomagnetic ratio, G factor, and the magnetic field H. This is how it looks like. This is the external magnetic field applied for several reasons. First of all, it is possible to solve the problem exactly when the magnetic field is applied. Secondly, the magnetic field, when it is applied, it gives us a natural direction for the quantization, for the spin quantization. Because otherwise, in the absence of the magnetic field, the way we choose x, y, and z axes in the spin space is completely arbitrary. Now, when the magnetic field is applied, it's most natural to talk about the projections of the spin, of the spins of the direction of the magnetic field. That gives us the natural definition of the quantization axis. So what we did last time, we said, let J be 0 first. So we have a set of independent spins placed in the magnetic field, therefore we have essentially a single spin problem. Because the Hamiltonian is additive, the energy represents an extensive quantity. Once we know the spectrum of a single spin, we know the spectrum of the whole system simply by multiplying the answer by the total number of spins, right? We know what happens here. It's a Zeeman splitting of the levels. But we may be interested in the dynamics of the spins, and what we were able to do was the following thing. In this specific case, we can see that the operator Sn plus, which was Sn x plus I, Sn minus, this index n, site index is irrelevant in this case because all of these sites are completely independent in this case. And the answer, the solution of that, yes. So what we do next, we built up this operator in the Heisenberg representation, Hz, T, Sn plus, minus I, Hz. This is Hz. This is Hz. This is the Zeeman energy. It's even Hamiltonian with the minus sign included, right? And if you do this, you will find out this is the initial value of this operator times minus I omega naught times time. This is how the dynamics looks like. So what it describes a precession of the spin which conserves the z projection of the spin. I have to put here S and Z E is equal to S and Z0, which means that it is not time dependent, it's conserved. What is not conserved, what undergoes rotation is a transfer, it's a projection of the spin onto the basal plane, xy plane, and that undergoes a rotation. The rotation angle phi being omega naught by t. So all the formula of the two-dimensional Euclidean rotation can be used here. So you have a vector which undergoes a rotation by this angle, and then you know how the x and y components of this vector are related. So this is what precession is about. This is the law of the precession. This precession, of course, is uniform. It depends on the initial values of the spin projections, and then the rotation goes precisely in the same way for all atoms, because the frequency is fixed. They all rotate with the same frequency. However, what happens when this is taken into account? I will not now derive all this in much detail, but because all these derivations are extremely simple, I will simply go now to the second case when J is now 0, and let me calculate the contribution of the exchange interaction into the spin dynamics. So in other words, what I need to do is to calculate the commutator Sn with the exchange Hamiltonian, and this is the exchange Hamiltonian. This part, the first term, is the exchange Hamiltonian. All right? Well, what I do, I simply take this construction, plug in, and honestly calculate the commutator of three speeds, SA, SB, SC, alpha, beta, gamma, generally speaking, right? So this is the structure which will emerge.
Alpha, beta, beta.
What?
Shouldn't it be alpha, beta, beta?
Yes, of course, but it's most general. It's more general. Yes, of course, right. It could be a little bit, of course, but the principle is very simple. So if you have A, B, C, the way you do it is the following. Let's say A, B, C, just to remind you something I believe you know anyway. You write down the ABC minus BAC, you subtract this, and then you add this, and then you add what remains. Here you see that C goes out, so it is the commutator of AB times C plus B and commutator AC. In other words, you follow the fate of the first operator, and then you commute it first with B, and then with C. And put the operator C to the right in the right-hand side, and then it will be in the left-hand side. So that's the simple rule. And when you follow this rule and follow the algebra, excuse me, the algebra of the spin operators, which you all know very well, then the result will be the following. This will go to J Sn cross, it's a vector product, sum over nearest neighbors S, N plus J, operator. This is how it looks like. So if I had calculated what I have already calculated, I didn't write it, if I had calculated the Sn with the Zeeman part of the Hamiltonian, then I will obtain something like Sn cross omega naught. That would be the result if I had kept only the Zeeman interaction. Then the result of this commutation would be just this vector product, which means simply tells you a very simple thing. This part has to do with time evolution because it originates from the time derivative of the operator in the Heisenberg representation. Now, what kind of evolution would you expect from the spin? If a spin is placed in the magnetic field, then the only thing which spin can do is undergo precession or rotation around in the direction of the spin. That's the origin of this vector product. So here it's a kind of tricky, as you see. At some point you can close your eyes and think of this term as an effective magnetic field, if you wish. So the structure, to make the structure similar, you find out that J times the sum plays nearly the same role as omega naught here, with the only but very important difference. Omega naught is an external parameter. It's a synonym. It's not an operator. Whereas here, this is an operator, so therefore I could have looked at this relation from the other side. I could put the minus sign here in front and bring us Sn to the right, and set the same words nearly as applied to Sn plus G. In other words, there is a clear indication what may happen. Since in the zero order approximation, saying basically we are in the ground state, we're looking only at the weak excitations. There should be a contribution coming to this expression originating from the fact that each of the operators has a non-zero expectation value in the ground state. The ground state is a state with a broken symmetry, right? The ground state is a state where the local operator is non-zero, and moreover, it is proportional to some vector E naught times some value of this S, or let me call it S absolute value. It is not, even though it is not a very good notation. But in this case, I would be inclined to identify E naught with Z with a three-dimensional vector 0, 0, 1, just because this is the direction of the external magnetic field. 0, 0, H. So the system polarizes along the magnetic field. I want to bring your attention to the fact, again, which gives us some similarity with what we have learned from lattice vibrations. Apart from this term, when this magnetic field is absent, what is written here? This is a construction invariant under arbitrary three-dimensional rotations. Right? If the spins were classical vectors, I would say this is a typical O3 group, O3 symmetry group. It's at all transformations with the vectors in Euclidean three-dimensional space, which keep the length of the vector and conserve relative angles between the two vectors. Scalar products, right? The standard requirement of how we define transformations of a vector space. Okay, but in the quantum case, this SO3 is replaced by the so-called SU2 group, SU2 symmetry, because the eigenvectors of the spin operators are not simple wave functions. Instead, they are spinors. They're multi-component wave functions, because the Z projection of the spin, the Z component of the spin may have two S+1 projections. All of them should be represented in this column vector. So this is spinor rather than the function spinor. But anyway, it's an isotropy group. If I turn to classical limit, it's a little bit not obvious. But we have already said that the ground state of the ferromagnet is classical. So therefore, we should not hesitate to apply classical picture when we are talking about the ground state. It's not a mistake, it's correct. So classically, we can think of some kind of classical vectors here and here. Full isotropy, all three groups. So I can think then that S goes to S magnitude times some unit vector E0, as I wrote here. And E0 is just the unit vector in this three-dimensional sphere. The length of this E0 is 1. This vector is normal to the surface and can be directed anywhere. So if I assume that the system undergoes a phase transition into an ordered state, this ordered state is characterized by non-zero polarization, non-zero average value of any local speed. Any speed on average, looks in the same direction. That gives you the total magnetization, which sums up this collective effect. It gives you a total magnetic moment of the whole system, which is huge, of course, and directed somewhere. The good question is where? Nobody knows. As long as magnetic field is absent, as long as that anisotropy is absent, you can't tell. Anywhere. So you choose some direction, and then you ask, what will happen if I rotate this to some other direction, call it E1? The answer is, the new state will be degenerate with the original one. That will have just the same energy. Because this is invariant under rotation. You perform a global rotation of all the speeds by a certain angle such that the magnetization moves from this direction to that direction. The energy is the same. So therefore, all of the points on the surface correspond to the same value of the ground state energy. So all this surface is the space of degeneracy of your Hamiltonian. How it's called. This is exactly how it's called in mathematics. The space of degeneracy. Right? As a consequence of that, since the symmetry group is continuous, and since each of the directions here breaks it, you have to have gapless excitations at low temperature. The only difference is with the phonons is that the spectrum of these gapless excitations is not linear, for the reason I have already discussed briefly. It has to do with the broken time reversal symmetry. But if you apply a magnetic field, the degeneracy is removed. In the presence of the magnetic field, no degeneracy is present. It's precisely the same effect as the one already discussed when we'll be dealing with the phonons. If you, instead of having a one-dimensional axis and put your atoms along this line and switch on this interaction, and there is nothing else but this interatomic interaction. Instead of that, if you put this potential, you by hand, you explicitly will break the original spatial translation of the areas. And the ground state will no longer will be degenerate, because the only thing which would be allowed is to place your atoms into the positions, into the bottoms of all the potential wells. This is precisely the same effect as if you have a direction of the magnetic field H, your polarization will follow this direction. This will be EH, and look along the magnetic field. The degeneracy will be removed. Now, why do you need it? It's a good, I slightly deviate, it's a digression from the main line, which I started with. Why do you need this? You would like to know whether or not the ground state indeed is infinitely degenerate. What you can do, there is a problem you will solve. I think one of those problems was on the list which I indicated in the beginning of the lecture. You switch on this field. And then you switch it off. And you ask yourself what remains. The answer depends where you are. If you are above TC, if the system is paramagnetic, and the temperature is higher than TC, then you polarize your system by external magnetic field. You see the response. You measure this magnetization. You find out it proportional to the field, with the coefficient being the susceptibility. And then you switch off the magnetic field, and the magnetization disappears. This is what paramagnets are about. They are only polarized when magnetic field is applied. But as long as the temperature is above TC. But if the temperature is below TC, it is not like this. You indeed cannot tell what is the direction of your spontaneous magnetization before you apply magnetic field. But when you do apply magnetic field, you enforce your magnetization to look along the field. Then be so kind, switch off this field. And this guy will remain. That's the notion of the broken symmetry. That the memory of the field still is here. The magnetization remembers what was the original direction of the field. You can solve this problem just for a single spin, say in the Ising spin in the magnetic field, and you will immediately reproduce everything I said right now, all the properties. And I suggest that you do it earlier or later. If you don't do it, I will ask you anyway. So better to do, yes.
So for the case that we turn on the magnetic field and then you turn it off, since the spins have new memory of the magnetic field, we can say that there is like a new ground state.
Well, this is a fixed ground state with a fixed direction of polarization. But you may ask the following question: how much energy would you need to overturn this total magnetization from one direction to another one? And the answer, I think you already know: zero. The collective excitation should exist, whose wavelength is infinite, who therefore discuss a uniform rotation, not a wave, but a wave with infinite length. The wave in the infinite length is a uniform process. It's a uniform rotation of all the spins, but since the frequency goes to zero when k goes to zero, the energy required for this rotation is zero. So this is why any point, any 2 points, any number of points on this surface are equivalent. They're all degenerate with the point of view of degeneracy. But there is an interesting issue, maybe you didn't come across your mind. If you take the quantum mechanical point of view and build up a quantum mechanical ground state for some direction of spontaneous magnetization, call it E0, let it be a ground state, wave function, or the vector state for the fixed direction of the total magnetization. And then you take another state, E1, which corresponds to another state, another direction of spontaneous magnetization. And you calculate the overlap of the two functions. And then the statement is that in the thermodynamic limit, when the number of spin goes to infinity, the right-hand side goes to suggestions, good guess, educated guesses. I want to hear from you. Irrespective of how small the relative angle is.
You don't throw the 2 people.
You should have anticipated. Please remember this is a result for the rest of your life. They are orthogonal. You cannot get from one, they don't even belong to the same Hilbert space. It's different Hilbert spaces. It's a very beautiful problem to solve. It's an orthogonality catastrophe. There is a problem of this form invented by Phil Anderson. We're all Phil Anderson lots of insights into condensed matter physics. You take a metal, no impurities, and calculate the wave function of the ground state. Then you put a single impurity, which scatters the electrons, different angles, whatever. It's a solvable problem. And calculate the ground state in the presence of the impurity. And then they calculate the overlap of the two wave functions. You get precisely the same result. These two ground states have nothing to do in common. They belong to different ground states. This is the famous orthodynamic capacity. And there are some kind of goldstones there as well, because it should be like this. It always has to do with some degenerates. Anyway, so I said about it enough, more than enough, and let me keep going. I don't need this, I don't need this. All right. So, if I do all these calculations, these are elementary, it's a simple calculation of commutators, according to the various prescriptions, what I will obtain. This will be, yeah, I wrote already here, yes, that's right, that's right. Yeah.
Why the condition n goes to infinity?
Why what?
Why do we need n to go to infinity for the...
Well, because it's everything we know in statistical physics has to do with the thermodynamic limit. The thermodynamic limit, we have the number of particles goes to infinity, volumes go to infinity. What is finite as the density is, and things like that. There are extensive quantities, there are intensive quantities. Energy is proportional to the number of particles. If you increase the number of particles, the energy blows up to infinity. Is of zero interest. There's no interest at all, interesting at all. So you have to look at the density of the energy density. This is why the thermodynamic limit is the law of large numbers. Because in that limit you can ignore fluctuations. In that limit, what you measure corresponds to equilibrium. Even the notion of equilibrium only is reached in the thermodynamic limit. That's the basics, one of the basic statements of quantum mechanics. All right. Yeah. So now, what is the idea? How to incorporate the idea 1/s expansion, which we have discussed before? How to make sure that indeed we can now take into account quantum effects in some kind of perturbative way. So we can do it in the following way. We can write down Sn as the average value of this Sn plus fluctuation. This average exists. And in the zero order, it's simply Sn times Ez. You believe that in the presence of the magnetic field, all the speed that chosen the direction, and take, on average, take the maximum value, which is the classical value of the average speed. And this deviation is the measure of quantum effects. It's a small addition, right? Now, when I have a product of these two operators here, I should realize that the vector product of the vector with itself is of course zero. That's trivial. It's very simple. The linear terms which proportion to S can be kept in a very simple way. What we will drop also is the product of the following structure. This will be dropped.
So basically what we are doing is the mean field.
Yes, of course it's a mean field. Yes, absolutely. Sure. We have to. It's a mean field, of course. It's a typical mean field procedure, as was correctly mentioned, in which we systematically drop the high order fluctuations, keeping them only in the linear order. If I do all this, I again will avoid details, but I can show in a very simple way that the vector product in this approximation of two spin operators as it's shown here, reduces to the difference Sn minus Sn plus G times vector product S is E. This is how it looks like. The derivation is elementary, and therefore there is nothing to comment on this. This is just simply a very simple thing. So we can write down now the whole result. The whole Hamiltonian will be given an approximation. And in this approximation, the result will look like, if I write down now, that's a bit more. If I write down now Sn dot, of course it's an operator. The result would look like J, S, Z. Z is the coordination number, which is twice the dimensionality. I assume that the lattice is a hypercubic lattice. And here I have Sn minus 1 over Z, sum over J, Sn plus J, such a structure, cross EZ, and plus omega naught, Sn, and cross EZ. This is the structure. So you see that the right-hand side contains the spin operators in the first power. There is no quadratic term, so that's the essence of the approximation. This is very much the same as what we had in bosonic terms. The structure of the excitation Hamiltonian in terms of bosonic creation and annihilation operator was quadratic. Consequently, the equations of motion must be linear. Right? If you have your Hamiltonian is quadratic, only in that case the equation of motion is linear. Otherwise, you will start generating triple terms, 5 order, 5th order terms, 7 order terms. So what is quadratic at the level of the energy becomes linear at the level of the equation. This is why quadratic Hamiltonians, these free particles, is the simply things which exist in physics. So this actually is the answer. This is already a solution, but not quite an appropriate solution because, first of all, from here we immediately see that the Z component, it was conserved, it is still conserved. The Z component is not time dependent, right? It's not vanishes because of the vector product. Is he here? Is he here? Only transverse components remains, right? So I can therefore rewrite everything what is written here in terms of transverse components. Here I will put the minus I, therefore. Here I will put S plus, minus I omega naught, S plus. I will remove this, of course. I will remove this, of course. I omega naught, and that's it. This is how the equation of the circular component of the spin operator, local spin operator, looks like. It's still not diagonal because of this term. And as usual, when we have something not diagonal in real space, we immediately pass to momentum space, make a Fourier transformation. So if you make a Fourier transformation in the standard fashion, we write down something like this, 1 over n, k, Brillouin zone, sk, an exponent, ikn. Then it's one line derivation, there is no derivation whatsoever. Okay, let it be dot, let it be minus I, epsilon of k plus omega naught sk plus. And epsilon of k, I don't want to write it down again, it's that very energy which we had derived using the second quantization bosonic approach. You remember the Hamiltonian, after diagonalization, acquired the form. It was epsilon of k, ak dollar ak, without 1/2. Oscillators without zero-point motion, which means classical oscillators. So the only thing happens is the addition of this extra piece. So in the absence of external magnetic field, the frequency as a function of k would follow the parabolic curve. When omega naught is not zero, it goes up. Well, then I can continue on anyway. K modulus. It acquires a finite gap of the order of omega naught. You remember analogy with this problem for phonons? For the straight line, for the full translational variance, we have linear dispersion for the form of acoustic phonons where this is present. What we have, it's a finite gap omega naught, which is omega naught is the eigenfrequency of each particular potential value associated with each other. So the same physics, the same phenomenon. Well, actually, this is the complete answer, because the solution of this is sk plus, as a function of t is sk0, and here we have minus I epsilon of k plus omega naught times 2. So if we didn't have an exchange interaction, epsilon k would be 0. And that would be the already well-known result, which describes a homogeneous, uniform rotations of all the speeds. The same structure survives the exchange interaction in the lowest order, but with the very, very important difference. Now the frequency of rotation becomes a function of k. And therefore, the rotation is no longer uniform. Different k's have different frequencies. So some spin components with a fixed k rotate fast, some of them rotate slowly, because the frequency is dependent on k. Right? Moreover, if I recall this definition, I therefore will attribute the picture which I would see in the real space to a superposition of effective spins, if you wish, which undergo precession in momentum space in a very non-uniform fashion. Different momenta contribute to this precession in different way. But essentially, it's again a precession. A precession around which direction? Around what? Around the effective internal magnetic field created by the spin polarization of all other spins except for of this one. Each spin can feel the essence of the effect of the internal magnetic field. So this is why the total field here is very frequently called the molecular or Curie field. The internal field or mean field, as your colleague has mentioned, is essentially of this origin. The very idea of mean field approach originates from this. So therefore, you can think semi-classically of spin waves as a superposition of inhomogeneous precessions, of local materialization, very much in the same way as you consider the normal mode expansion of the displacement field for phonons by expanding each pattern of oscillation into elementary waves, and then taking the linear combinations. And then what you get is very In real space, maybe it may look very, very complicated, but in momentum space, it's a very simple thing to do. So basically, that's it with the ferromagnetic phonons. We cannot tell much more than on that, but we will have a lot of problems to solve. All the rest will be delegated to the problem. So I will make you very happy. So you will start looking at these problems. You will understand it's a rich subject. Okay, any questions for ferromagnetic spin waves or magnons? So please keep in mind, magnons or spin waves, there's identical nomenclature, it's the same. So two different ways to say the same thing. Magnon appears as a quasi-particle. For a magnon, it's easier, it's more natural to use this language, to assume this. This is the energy of the magnon. Magnon K is the momentum of the magnon. AK and AK dagger are creation-annihilation operator for the magnon. Magnon is a quasi-particle. When I look at this, it more comes to me as an association with the spin wave, because it looks like a wave. Like a precessing magnetization appears as a wave. So, but it's essentially the same. Different languages of the same phenomenon. All right, so now we're now turning to even a more interesting issue, quantum antiferromagnet. The field of quantum antiferromagnetism is vast, it's very interesting, it's very complicated, and not all the problems have been solved so far. There's been done a lot of progress, of course, but there are still issues far from being solved completely, even understood. So, the homotopy of a quantum antiferromagnet is this. M and M are nearest neighbors, and J is positive. For future purposes, we'll again assume that the spins are large, just to make sure that semi-classical picture works. But it turns out that the sign, the change of the sign, is dramatic. It leads to a completely different physics. Completely. First of all, the result of the analysis which follows essentially depends on the type of the lattice you're dealing with. So if you take two spins, S1, SS2, and look at this interaction, then for J positive, you would prefer that these two spins are antiparametric. If you take the value of the spin to be 1/2, okay, you would say this should be a singlet state. These two, the ground state should look at a singlet state, up, down, minus, down, up, square root of 2. Singlet state. Right? Very nice. Now imagine that your lattice is triangle. 1, 2, 3. You take a pair 1 and 2, and you build up a state. Suppose you put up here, then you put down here. You take a pair 1 and 3. You took up here and put down here. You took 2 and 3, you see, the two are parallel instead of being antiparallel. And this is phenomenon is called frustration. It's not the literary term which reflects the depressive state of a human being, but it's a depressive state of physical object. It's in depression because it cannot realize the antiferromagnetism. It can't. Whether you put down here or up here, it's just the same as frustration. Who invented this term? You must give a very educated guess. So many things are due to this gentleman. Phil Anderson, of course. Who else? Him, of course. So we do not consider this issue because fluctuations here are extremely strong, not only because of the quantum nature of the phenomenon, but also because of the geometry of the lattice. We will not consider this. It's a special branch of physics, perhaps not for the postgraduate diploma students, maybe a higher level, yes, but here, only a kind of private discussion. Visit me in my office, I will tell you. We will assume that the lattice has a very important property. It is divisible into sublattices, 2 or more sublattices. For instance, this is a typical lattice, which has a property of being bipartite, which means divisible into sublattices. For instance, if I call these sides A, and then I call these sides B, then I will say that the whole lattice represents a superposition of interwoven lattices, also cubic lattices, but you can see that to imagine, right? So you put one internal, so if you have 2 different atoms, A and B, or 2 different spins, or 2 different spin configurations, or configuration is such that the spin orientation here and here are different, then the elementary unit cell contains 2 atoms necessarily, not 1. So the unit cell is 2 atomic cell. It's already a new thing to deal with. So this is one of those possibilities. The other is the so-called honeycomb or hexagonal lattice. Let me sketch its structure. It's also divisible into A, B, A, B, B, A, B, B, A, B, and so forth. So the distinctive feature of the bipartite lattice is if you take an atom and look at its nearest neighbor, so if the original atom belongs to sublattice A, all the nearest neighbors will belong to sublattice B, and vice versa. For simplicity, we will deal with the lattice like this, which is a hypercubic lattice. In this case, it's a square lattice. But in any case, the bipartite nature of the lattice will be assumed. The frustration will not be discussed at all. Now, semi-classical. If I have on A sublattice the spin S, then the interaction, which is antiferromagnetic, suggests that on the B sublattice I should have the spin minuses. And this is what is called the nail state. It's a classical nail state. So if I, just to make sure that I can visualize everything, if I take the spin 1/2, then I have a picture plus, minus, plus, minus, minus, plus, minus, plus, plus, minus, plus, minus, minus, plus, minus, plus. Of course, the speed is 1/2, the speed is much larger than 1/2. But to me, it's just somehow easier to draw. Here, of course, I can assume that plus is S and minus is minus S, but then in between there are 2S minus 1 possibilities. I don't want to deal with them. I want these 2 orientations to be only allowed orientations, just to explain some certain things about the antiferromagnets. So when I draw plus and minus, or when I write down, why didn't you tell me that left-hand side is a vector, the right-hand side looks as a scalar? When I was a student, I was witnessing a discussion with our favorite professor who was examining another student, and who wrote something like this. He was thrown out immediately out of the room. Immediately. He would forgive whatever you want, but never if you write down a vector in the left-hand side and a scalar to the right-hand side. You're out. Because the vector contains more than one component. The two things that cannot be equal to one. So therefore, you should immediately interrupt me. Why you didn't do that? I deserve to be thrown out for this stupid thing. Yeah. Okay. Anyway. Now look. Once I chose the quantization axis, this is the quantization axis. I can separate z component, the interaction of z components of the spins from the transverse component, exactly in the same way as we did for the ferromagnet. So we will write down something like J and M, S and Z, S, M, Z. This is fine. And then I will write down 1/2 Sn plus, Sn minus, plus, Sn minus, Sn plus. So this is basically the interaction of XX and YY components, right? So rewritten in terms of the circular component. And then we said, okay, we know that this is essentially a classical part of the Hamiltonian. Because it measures the spins in the ground state of the system, and of course it will give me minus S squared times the number of pairs, nearest neighbor pairs. Well, that's an easy thing just to do. S squared order of the system. Now let me see what is the result of acting of this part of the Hamiltonian onto this state. In the in the case of a ferromagnet, the result was 0. Because there is no process in quantum mechanics when two spin ups can transform simultaneously to spin downs. It is always like this. One goes up, the other necessarily goes down. Total spin, Z component conserved. But here I can imagine that if I take, for instance, this pair, what I will obtain this configuration. You see? I will create two wrong pairs of the spins. Which means that if I build up by hand such a state cannot be an eigenstate of this operator. Because this operator acting on this state creates this state. And then I would have to write down the action of the Hamiltonian onto this state. It will again bring me back to the state and create something new. And it will be a chain process. I will never stop. Which simply means that whatever I started from, the initial state, is not an exact state, an exact eigenstate of the antiferromagnetic quantum Hamiltonian. So therefore, we have to work out how the correct ground state looks like. And we immediately realize that quantum effects are important not only at the level of excitations, but already in the ground state. The classical ground state is wrong. Sometimes it is completely wrong. By saying wrong, I mean the null state is a semi-classical or classical looking states with spin up and spin down. By up and down, now I mean S and minus S. Is the spin is large enough? And if the dimensionality of space is large enough as well, then such state is stable. It will be subject to some corrections, to some renormalizations. The magnitude of the spin will be decreased by quantum fluctuations, but still survive, will still survive. You will have a null state, a semi-classical state, which is basically stable. But if you go to the one-dimensional space, for instance, and take the worst case for the spin, spin 1/2. It's the minimal speed, not the quantum speed from time. It turns out whatever follows, whatever I will discuss with you today, is completely wrong. There is no long-range order, not only at a finite temperature, but even at 0 temperature. Fluctuations wash out any kind of ordering completely. And that's a typical quantum field theory which starts. And this is why what we do in condensed matter physics, especially in low dimensions, is so close to what is being done in high energy physics. Very much the same. Very much the same. So, now our problem is just to do our job in the same way how we did before. But the important difference, the difference originates from the fact that in the ground state, the A sublattice has spin up and the B sublattice has spin down. And therefore, if I want to follow the Holstein-Primakov, N belongs to A sublattice. For A sublattice, S and Z, I can define essentially in the same way as before. I can think of the classical value of the spin minus certain amount of excited magnons, if you wish. Small amount, of course, as compared to S, but fine. And of course I have to write down Sn plus, and if I want to, Sn minus. If I want to rotate my spin, I want to decrease its value from maximum. I have to create, I have a created boson, therefore it should be this, and Sn plus should be square root of 2s, Sn. This is what we had for a ferromagnet. So I take the sublattice. So in fact, in a semi-classical description of a ferromagnet, I have a superposition of two ferromagnets. Each sublattice represents a ferromagnet, but interaction couples them. That's the point. If they are completely decoupled, there will be no problem whatsoever, but interaction couples them. Now it's the second case, M. Site belongs to B. Then I write down SMZ. It starts not with S, but with minus S. It goes down. Right? Now if I want to build up an excitation on the B sublattice, I have to replace minus S by minus S plus 1, or plus 2, or plus 3. So I add phonons. Backwards. I call them B. And now, every time I do this, I increase the number of magnets, and here, if I want to decrease it, it's just the conjugate. Is it clear what I wrote here? These two interchange, they look different. These and these look differently. A dagger and the A and the Any questions? Yeah, it's very important. Again, this is S. This is A sublattice. You consider excitations. This is S minus 1, S minus 2, and so forth, right? This is minus S. This is minus S plus 1, minus S plus 2, and so forth. Every time I write down, subtract minus 1, minus 2, I can think in terms of certain numbers of bosonic modes, which take value 0 for the ground state, 1 for the first excited state, 2 for the second, for the next, and so forth. I do just the same here for the B sublattice, but I increase the projection. So therefore, I have to add, not to subtract, but add bosons. And the same here, every time I decrease S here, I create boson. Every time when I increase the spin on the B sublattice, I create boson. That's the essence. Right? Okay, good. Now, what do I do next? I simply take this. Everything is already written as it should be. I have all the expressions for the components of the spin operators on the two sublattices. I plug in, keep the terms of the S squared, which will be the ground state, keep the terms of the order S, that will be excitations, and drop the terms of the order of 1. That will be a quartic terms in terms of A and B. 4 order terms, I throw them completely. What remains is the following, just I leave it to you. First of all, you calculate the classical contribution of the ground state energy, but it's not the true ground state energy, it's the energy, ground state energy for the Nair state, for the classical Nair state, for this state, which is not the ground state. And it is minus J and S squared and D. So therefore, my total Hamiltonian decouples into the ground state energy and plus the contribution of fluctuations. It's not the excitations, not so. I cannot call it excitations as I did for the ferromagnetic magnets. Why? Because the fluctuations and excitations were identical motions. Here fluctuations will renormalize even this. They will work both into backward direction. They will alter the structure of the ground state, as well as define the structure of excitations. This and that, both. Why we should do that? Because this is unacceptable, as I told you last time. In quantum mechanics, there is no notion like S squared. There should be SS plus 1. And since the ground state is quantum, be so kind, find the way to replace S squared by SS plus 1, but not by hand, but you have to derive. And one of the points of this derivation will be to see how the S or the correction will add to this one, because SS plus 1 is simply S squared plus S. Second order from here, S from fluctuations, that gives you SS plus 1. All right? So you see how smart the theory is, how it's well built. A serious theory, a real theory, very powerful theory. Everything, those guys have been thought about everything on it. Okay? So if you do this, then you will find out a very simple thing, namely that your fluctuation part, looks as JS double sum N, M. Here we go, A, N dagger A, N, this is fine, A, M, excuse me, B, N dagger B, N. N and M are nearest neighbors, N belongs to A sublattice, M belongs to B sublattice. Here I have A and BM, and plus A and dagger, B and dagger. That's the new structure of the fluctuation part of the Hamiltonian in terms of the two groups of bosonic operators, A and B, defined corresponding on the A and B sublattices. Well, one thing is nice and expected. The expected thing is that it's a quadratic form. Well, we did everything to keep the form quadratic. we intentionally by hand have thrown out everything which was not covariant. But on the other hand, well, it is these two pieces are side diagonal, and therefore they don't describe anything which propagates. Because if I pass from real space representation to momentum space representation, I have a trace here, I will have trace there as well, both in real space and K-space. But here, N and M are different sides, and A and B are different particles of different natures. So there is a propagation here, but of what kind? My God, the particle number is not concerned. Not a structure A dagger B or B dagger A. I can build up an operator. NA, sum over all latest sides belonging to A. A and dagger A, A. And I can also build another operator, particle number operator, the one which counts the number of bosons on the B side. Now imagine that I have a sum of this structure. Imagine. It could have been, by the way. There are some problems which reduce to this, what I am writing out now. It's a nice expression. A transforms to B, B transforms to A. There are transitions between A and B sublattices, but what is important, NA separately is not concerned, because A particle transforms to B particle. In other words, this is a process when AA is replaced by NA plus 1, and in B is transformed to NB minus 1. Here it is just the other way around. It will be plus here and consequently minus here. But the sum and total will be conserved, because I can only regroup the particles between the subgroups, the total number being conserved, right? If I have this structure, if, but I don't have one. Instead of this, I have this one. I have a process, NA goes to NA minus 1, and B goes to NB again minus 1. So the total particle number in this process goes to N minus 2. And quite similarly, it will go to plus 2 as well. The particle number is not conserved, only parity is conserved. Today we would say, okay, perhaps this should be an indication of some non-trivial topological properties, in fact. But that's a different problem, we will not touch upon it. The total particle number is not conserved, which means you have to say goodbye to any unitary transformation to diagonalize your multiplier. Do you agree with me? Because unitary transformations are supposed to, always are invented to conserve the total particle number. And this is the problem only if this number is not conserved already at the level of the Helmholtz formula. What is that transformation? Non-unitary. But on the other hand, should be canonical transformation, which keeps the algebra of operators intact. So this is called the canonical transformation, but not unitary transformation. And this is one of those transformations are known under the name of Bogoliubov transformation. So I'll write down this name because we have to remember it. So, was a great mathematician and physicist, theoretical physicist. So the first thing we do is the following. First of all, I will say a few more words, and then we'll derive the rest during the next lecture. By the way, our schedule for the rest of our activity will be as follows. We will carry on today. We'll already almost finished with the Monday lectures. We'll have 2 more on Wednesday and Friday. Now, next Monday, we'll organize a tutorial, because by Friday, you remember you are due to, your homework is due by Friday. By next Monday, we'll have a full picture of your activity both on phonons and magnets, right? And we'll organize a tutorial. We'll discuss some questions which are left over, will be important. And then next Wednesday, we'll have a midterm exam. Next Wednesday.
1 week.
Yes. 7 days plus 2. Right? And then Monday will continue as follows. And before the final exam, we'll have the second tutorial. We will summarize everything, and then, if I'm not mistaken, by 3rd of March, we'll have a final exam. It will be a written exam with some questions on theory, but mostly and dominantly on problems. All right. Okay, so maybe I can stop even at this point. The only thing I will need to tell you, just to explain a little bit, it's of course we will need first, before doing any transformation, first to move to momentum space. But when moving to momentum space from the lattice, we need to use the brilliant zone, and you have to know what is the symmetry of the original lattice. Now, if we put this black dots and white dots, this is for A and this is for B, in the following way. We see that we have 2 different atoms, A and B, because with these 2 atoms are associated 2 different values of classical spins, plus S and minus S. These are in the Néel state, right? So if I take this unit cell, as it is, this unit cell is a standard crystallographic, crystalline unit cell. It does not effectively distinguish between A and B. It contains 1 atom, 1 site within it, because it enters with a weight 1 quarter, 1 quarter, 1 quarter, and 1 quarter. We have to take into account the number of the squares shared with the given one. So the magnetic unit cell is this. This is A. This is A, and there is a full atom completely inside this. By 1 quarter each of the A atoms is here, so altogether I have 1 A atom and plus 1 B atom. 2 atoms altogether. So this is a magnetic unit cell. This is the original crystallographic unit cell. What we need is this, not this. Because everything, these operators parameterize the spin operators. And the spin operators in the ground state display this Néel structure, plus minus, right? So therefore, the number of magnetic unit cells n prime will be n divided by 2. Right? Because each such sites takes upon itself 2 sides rather than 1. This should be kept in mind. So in other words, if I write down, for instance, the Fourier transform for the AN operator, Fourier transformation, I will first of all write down the square root of n prime rather than n. All operators are defined in the brilliant zone, in the magnetic brilliant zone. Let me call it BZM magnetic, right? Here I will write AK. IKN, and NSN belongs to A sublattice, and I will just precisely the same for the B. And then I will plug everything in here. And I will find out the K is very well defined quantum number, goes through the whole construction as a parameter. Everything is diagonal in K, but not diagonal in A and B. Particle numbers are not concerned. There I will introduce the Bogoliubov transformation. So this is the plan of the action, and this is enough for today. If you have questions, just ask me now. Yep.
When we try to build the thermodynamics of magnets,
Thermodynamics of
magnets,
fine.
the thing is that the thermodynamic average of A dagger A
Uh-huh.
cannot be arbitrarily large
Why not?
because the Holstein-Primakov.
Oh yeah.
So why can we substitute it with boson?
Well, because no, you can't substitute. Okay, well, you're asking the same question as I emphasized on Friday, I believe. I said there is no direct and exact correspondence
Yes.
between the spin operators and the bosonic operators. For the very simple, if not to say trivial reasons, because the dimensionalities of the corresponding spaces are different qualitatively. The spin Hilbert space is finite dimensional, and the Fock space of the boson is infinite dimensional. You cannot map anything finite onto infinite. It's impossible. Because infinity is more powerful. So therefore, it still makes sense to calculate the thermal average of the bosonic occupation number, as long as your theory doesn't deal with triple or quartic terms. You cannot do calculations with 4 A operators and be sure that you are doing the right thing. As long as your thermodynamics will reduce to calculating averages of bilinears of these A or B operators, including A dagger A, B dagger B, A, B, or B, B, or A dagger, B dagger, you are on safe ground just to make sure that with your temperature analysis you don't go too high in temperature
Yes.
as compared to nail temperature.
So the temperature limitation allows us to use the exact
You
terms
can
of this
only
equation.
use the region of the temperature well below the nail temperature. You cannot even approach nail temperature. You cannot describe criticality. You can't do that. You are deep inside the classical ordered phase, and you can ask only to what extent this classical state is stable. It inevitably undergoes transformations and renormalizations, but do these renormalizations ruin the classical state or no? Destroy? No, they don't if the dimensionality is large enough and if the spin is large
And
enough.
one more question.
Yeah.
The similarity between spin 1/2 antiferromagnet on one-dimensional chain and the instability of one-dimensional harmonic oscillator chains.
No. Well, the instability, the similarity is only in the following sense. One-dimensional space is most vulnerable, most sensitive with respect to fluctuations. In one-dimensional space, whatever the symmetry group, fluctuations are the strongest possible. It's well known. Because there are only two neighbors, if you wish. There are no loops on the one-dimensional space. The loops are very important because if you can connect yourself with the loop, then you are stable, in a sense. There are no loops in 1D. There is even no notion of statistics in 1D because two particles cannot be interchanged without hitting each other. There is no loop. So division into fermions and bosons is based on the properties, transformation properties. So the wave function under exchange, but the exchange is always going along closed trajectory. There is no closed trajectory. They hit each other. Therefore, you can always say that fermions are the same bosons, but with infinitely strong interaction in 1D. It's very fair statement. But your statement was basically to what extent the absence of the latest thing there and the here is the same. Not exactly, because after all, that symmetry was abelian and this is not.
Sorry?
That symmetry was abelian, commutative symmetry. There is no non-abelian symmetry in the lattice vibrations. There is a continuous group, translations, okay, three-dimensional translations,
Yes.
and one-dimensional translations.
But
It's not like Rubik's Cube, you know. Rubik's Cube deals with the discrete, but three-dimensional by rotations. Rotations form a non-abelian, not commutative. So therefore, here, what happens here is, as your group is non-abelian, as a consequence of this non-abelian nature, not only the long-range order decreases, but it decreases in a different way. The way it decreases is different. It is very similar, but not exactly the same. Well, for instance, the number of Goldstone modes are 2, not 1.
In one-dimensional chain, when the symmetry is spontaneously broken.
It cannot be broken, and no continuous symmetry can be spontaneously broken in one day. You must have an Isaac symmetry, a discrete symmetry, which can be broken spontaneously, and only in the ground state.
Yeah.
Here you cannot, even though you can't do that in the ground state. Okay, well, you are right in one sense. In both cases, the ultimate reason of destroying long-range order, even at 0 temperature, is quantum fluctuations. This is, you can tell for sure. These quantum fluctuations show up more or less in the same way as Goldstone modes, if you wish. Both there and here. There is still certain differences in the symmetry structures of the both theories. The first theory deals with the nonlinear sigma model. You have a compact manifold, which is three-dimensional. You consider different trajectories on that, and you derive there are lots of Hopf terms and topological terms, and this quantum field theory is much richer for the spin chain rather than the trivial lattice vibrations. And the reason is non-abelian character of the group. The group is non-abelian, non-commutative, I suppose. No questions?